Welcome to this video where we're going to take a look at the binomial expansion of x plus y to the power of n with n a positive integer or 0. The binomial expansion of x plus y to the power of n with n a positive integer or 0 is a big part of the A-level maths course. On the screen now is the formula that you need to know and be able to use as part of your course, where the expressions nm are said n choose m represent the binomial coefficients and which are sometimes written NCM. I personally prefer the notation NM, so that's what I'll tend to use the majority of the time and certainly in this video. This formula can be written more succinctly using sigma notation as shown on the screen now. And of course there are some parts of the expression which can be expressed in a simpler form. For example, n choose 0 equals n choose n equals 1. N choose 1 equals n choose n minus 1 equals n. X to the power of 0 equals y to the power of 0, which of course both equal 1. X to the power of 1 equals x, y to the power of 1 equals y, and so on. Also, the binomial coefficients can be replaced with either n factorial over k factorial times n minus k factorial, or there's another form which is n times n minus 1 times n minus 2, up to n minus k plus 1 over k factorial. And therefore we can write the formula for the expansion of x plus y to the power of n as shown on the screen now. And it really doesn't make much difference at all which form you personally prefer to work with. They all amount to pretty much the same thing and will all lead to correct results if used properly. You'll probably come across all of these variations of the formula and others besides as you go through your A-level maths studies. So let's jump straight into some examples. The best advice that I can give when calculating the binomial expansion of an expression is to really take your time and don't try to do too much at once, especially in the early stages. Your confidence and along with that your speed will naturally improve with practice. Question 1. Find the binomial expansion of 2 plus x to the power of 6. In this example we have the x from x plus y to the power of n replaced with 2, y from x plus y to the power of n replaced with x, and of course n is equal to 6. So therefore for the first step it's simply a case of substituting these values into whichever your preferred formula for the binomial expansion is, and I'm going to use the first formula to give 2 plus x to the power of 6 equals as shown on the screen now. And so making some simplifications, we get 2 plus x to the power of 6 is equal to, as shown on the screen. And finally, simplifying each term fully, we get that 2 plus x to the power of 6 is equal to 64 plus 192x plus 240x squared plus so on. Question 2. Find the binomial expansion of 2p minus 3q to the power of 4. In this example, we have the x from x plus y to the power of n replaced with 2p, y from x plus y to the power of n replaced with minus 3q, and n equals 4. And so x plus y to the power of n becomes 2p minus 3q to the power of 4, whose expansion is as shown on the screen. Doing some of the simplifications gives that 2p minus 3q to the power of 4 is equal to as shown on the screen, and simplifying each term fully gives that 2p minus 3q to the power of 4 equals 16p to the power of 4 minus 96p cubed q plus and so on. In some cases you may only need to find part of the binomial expansion. Question 3. Find the binomial expansion of 1 plus 4x to the power of 10 in ascending powers of x up to and including the x cubed term. In this example, we have the x from x plus y to the power of n replaced with 1, y from x plus y to the power of n replaced with 4x, and n equals 10, giving 1 plus 4x to the power of 10 equals as shown on the screen. We don't need to go any further with the expansion since we only need to go up to the x cubed term. So we have, after some simplification, 1 plus 4x to the power of 10 is approximately equal to the expression shown on the screen. And then finally, 1 plus 4x to the power of 10 is approximately equal to 1 plus 40x plus 720x squared plus 7680x cubed. The binomial expansion of x plus y to the power of n has many symmetries that in some cases you can take advantage of. For example, If instead of writing the expansion in descending powers of x and ascending powers of y, from left to right, we could, without making any other changes, interchange x and y and write the expression in ascending powers of x and descending powers of y, giving the expression as shown on the screen. Also, the binomial coefficients are symmetrical in that we have n choose k is always equal to n choose n minus k. So in effect, it's only really necessary to calculate about half of the binomial coefficients in a given expansion. And as you become more familiar with binomial expansions, you may also see other patterns and symmetries that you can use to your advantage. Through practice solving problems, you'll just naturally pick up on certain patterns and start to use these to speed up your working. Let's have a look at some more examples, and in these examples I'm going to go into a bit more detail with my explanations of the solutions. The questions and problems are ones that I've just come up with and may not exactly be exam style, meaning in an exam you may or may not be given more guidance and so on. In my explanations to the solutions to these problems, I'll be trying to articulate to the best of my ability how I'd personally go about solving the problems. I'll be trying to explain the kinds of things that I see, maybe why I consider these things important or relevant and so on. And I'm not making any claims that the way that I solve these problems is the only way or the best way, just a possible way. Question number 1. Use the binomial expansion for 2 minus x to the power of 8 to find an approximation of 1.99 to the power of 8, correct to 4 decimal places. So from the outset with this, I can see that 1.99 is equal to 2 minus 0.01, in which case x is going to be equal to 0.01. So I'm already predicting where this is likely to go, and it's important to try to develop to a certain degree an ability to predict where things are going to go with your solution to a problem wherever possible. This just takes practice. In any case, I need to find at least a partial expansion of the binomial expansion of 2 minus x to the power of 8, and I'll want the expansion to be in ascending powers of x. Note that as the power of x increases, then for x small, and in this case I'm expecting x to be equal to 0.01, then the increasing powers of x will rapidly become smaller and smaller, and thus will become, let's say, insignificant. So we get 2 minus x to the power of 8 is equal to the expansion as shown, in an unsimplified form. If we do have x equals 0.01, then x squared is equal to 0.0001, x cubed is equal to 0.000001, and x to the power of 4 is going to be 0.0000, however many noughts, with a 1 on the end. And so there's no real point in going beyond the x to the power of 4 term, because adding these higher power terms is not going to affect the value of the digit in the 4th decimal place. So we have that 2 minus x to the power of 8 is approximately equal to 256 minus 1024x plus 1792x squared minus 1792x cubed plus 1120x to the power of 4. And so substituting x equals 0.01 gives 2 minus 0.01 to the power of 8, which of course is equal to 1.99 to the power of 8, is approximately equal to 256 minus 1024 times 0.01 plus 1792 times 0.01 squared, and so on. And so 1.99 to the power of 8 is approximately equal to 245.9374192. And so 1.99 to the power of 8 is approximately equal to 245.9374, correct to 4 decimal places. I would expect in an exam situation that you would be given more of a clear indication from the outset about which terms to include in your expansion. For example, find the binomial expansion of 2 minus x to the power of 8 in ascending powers of x up to and including the x to the power of 4 term, or something along those lines. And of course, this kind of method for approximating the values, such as 1.99 to the power of 8, is fairly obsolete and redundant now with calculators being widely available. The importance of such a technique would have been much greater back in the day, I suppose. But nevertheless, this is an application of the binomial expansion, and despite its practical redundancy, it still highlights how binomial expansions can be used. Question 2. Find the coefficient of the x term in the expansion for x plus 1 squared times 1 minus 2x to the power of 5 all squared. Okay, so one of the worst things you can do here is to just start expanding everything out willy-nilly. Don't bother, because it'll take forever and it's a waste of time. Think carefully about what you have and try to plan ahead a bit. There's surprisingly little work involved in this, so let's have a look. Since I'm interested in the coefficient of x, then I don't need to worry at all about any powers of x greater than the first power. In other words, I need only worry about constant terms and x terms. So I'll start with the expressions inside the square brackets. That's x plus 1 squared, which, of course, I don't really need to use the binomial theorem to expand this, and 1 minus 2x to the power of 5. And I'll only need partial expansions of each of these in ascending powers of x, up to and including the x term. That is, each expansion need only be of the form a plus bx. So partial expansions in ascending powers of x up to and including the x term for both of these are x plus 1 squared is approximately equal to 1 plus 2x, and 1 minus 2x to the power of 5 is approximately equal to 1 minus 10x. And so I can find the partial expansion of x plus 1 squared times 1 minus 2x to the power of 5 in the form a plus bx, which of course I find to be 1 minus 8x. And so we can find the coefficient of the x term of x plus 1 squared times 1 minus 2x to the power of 5 all squared simply by considering the expression 1 minus 8x squared, where the x term will be minus 16x. And so the coefficient of the x term is just minus 16. So what's the point of doing all of this? Well, at this stage, the point of getting you to do these things, what we did in the previous example, finding the coefficient of a specific term in an expansion, as far as I can see, is really just to get you thinking more carefully about what you intend to do, since if you just dive straight in and start expanding all over the place without giving any thought to what you're doing, then you'll create a huge amount of unnecessary work for yourself. Try it in the previous example and see for yourself. And so, to solve the previous problem effectively, you have to be able to plan your solution, anticipate how things are going to go, and distinguish the relevant from the irrelevant. So now we come to the part of the video where we kind of go off script a bit and explore the concepts introduced in this video in a bit more detail, and that usually entails going beyond the requirements of the A-level specification. The material in the rest of this video is not, strictly speaking, necessary to your A-level studies. However, by understanding even some parts of the extra material, it may allow you personally to understand A-level mathematics on a deeper level. So let's get going. Binomial expansions are concerned, as we've seen, with expansions of expressions of the form x plus y to the power of n. And in this video, where n is restricted to being a positive integer or 0. If, for example, we expand x plus y squared, we obtain the expression x squared plus 2xy plus y squared. If we expand x plus y cubed, we obtain x cubed plus 3x squared y plus 3xy squared plus y cubed. And as a further example, in the case of x plus y to the power of 4, we get x to the power of 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. Of course, we could continue expanding brackets and seeing what we get in each case, but what we really want to do is to try to extract a suitable pattern that may allow us to express a general formula for the expansion of x plus y to the power of n. And this is a very common thing to do in mathematics, trying to find general patterns. That is, to look at some specific cases and try to see if there's an obvious pattern that emerges. Clearly, this in itself is not enough to guarantee that the pattern is a general pattern. Just because we think we've observed a pattern for a few specific cases doesn't mean that the pattern always holds, even if it does in these particular cases that we happen to have tried. Nevertheless, this is often a good place to start. Patterns can be easier to see when considering a few specific cases, And this might give us the direction that we need in order to go on to further investigate whether that pattern holds more generally. An observation that we may make here is that in the case of x plus y squared, we obtain an x squared term, an xy term, and a y squared term. In the case of x plus y cubed, we see an x cubed term, an x squared y term, an xy squared term, and a y cubed term. And finally, in the case of x plus y to the power of 4, we have terms in x to the power of 4, x cubed y, x squared y squared, xy cubed, and y to the power of 4. Therefore, we might postulate that in the case of x plus y to the power of n, we'll have a term in each of x to the power of n minus r times y to the power of r for each integer r with 0 less than or equal to r less than or equal to n. But what will be the coefficients of these terms though? Well, if we think of x plus y to the power of n as the product of n factors of x plus y as shown, then notice that when we expand the expressions, x plus y squared for example, we can write this in an unsimplified form as xx plus xy plus yx plus yy. We can write the expansion of x plus y cubed as shown, xxx plus xxy plus xyx and so on. And for x plus y to the power of 4, xxxx, xxxy, and so on. Meaning, in the case of x plus y squared, we have sums of strings of symbols, x and y, of length 2, accounting for each possible combination and with no duplications. In the case of x plus y cubed, we have sums of strings of x's and y's of length 3, again accounting for each possible combination and again with no duplications. And similar comments apply to x plus y to the power of 4. Therefore, we might reasonably expect that the expansion of x plus y to the power of n to be, in an unsimplified form, a sum of strings of x's and y's of length n, where every possible combination appears exactly once. So now we'll collect together all the combinations consisting of strings of n x's, of which there's only one possibility. There are n possible ways of forming a string of n symbols consisting of n minus 1 x's and 1 y. And more generally, if we have a string of n symbols with n minus r x's and r y's, there are n choose r possible combinations where n choose r is equal to n factorial over r factorial times n minus r factorial. And this is said n choose r. And n and r are non-negative integers with r less than or equal to n. And therefore the expansion of x plus y to the power of n can be simplified by collecting together all the like terms and writing them in index form, and we obtain the expression x plus y to the power of n equals the sum from r equals 0 to n of n choose r times x to the power of n minus r times y to the power of r. And that's it. That's our general formula for the expanded form of the binomial expression x plus y to the power of n. The numbers n choose r in this context are often called binomial coefficients. Now what we've done here still doesn't constitute a proof of this general formula. We've identified what we believe to be a pattern that holds generally, and we've found a way to express that pattern, but it's still necessary for us to prove in a mathematically valid way that this pattern does actually hold in general. So how might we do this? Well, I'm not going to go into the details in this video, but one very common way of proving that this formula holds in general is using the technique of proof by mathematical induction. This technique is usually covered on the A-level further maths course, and it's a very powerful and useful technique for proving theorems in mathematics. So that brings us to the end of this video. I hope that you found this video useful, and if you have any questions about anything in this video or about mathematics in general, then please feel free to drop me an email or leave a comment in the comments section. Please subscribe to my channel and hit the like button to show your support. Thank you for watching, and I'll see you in the next video.